All right, so here are some the hints for homework 16, which of course is chapter 15, which deals with the death of stars. So right here we have the density of the white dwarf. The first question is about a white dwarf. Is the mass of the white dwarf divided by the volume? The mass has to be in grams, and the volume has to be in cubic centimeters. So how do we get the volume? The volume is, for a sphere, for any sphere, the volume is 4 times pi divided by 3 times the radius raised to the third power, where the radius has to be in centimeters. All right, so the first part, they give us the radius of the white dwarf is approximately, um, 10,000 kilometers, which is another way of writing it is 1 times 10 to the fourth kilometers. If you remember that little trick, if you don't, just remember this, to convert kilometers into centimeters, whatever it is, like if this was 3,000, three times 10 to the fourth kilometers, you would just, say, you just multiply whatever the exponent is times 10 to the fifth, right? So in this, if it was 3 times 10 to the fourth, it would be 3 times 10 to the ninth. But this one is just 1. I was just using an example there. This one is just 1 times 10 to the fourth. So 1 times 10 to the fourth times 10 to the fifth, right? Which converts it from kilometers to centimeters. Just becomes, of course, 10 to the fourth times 10 to the fifth. You just add the exponents, and so that becomes 1 times 10 to the ninth centimeters. Now, then you have to cube that. And then multiply by 4 pi divided by 3. So that will give you the volume that you put into the denominator in the density equation. The mass is given to us as 1 solar mass, which of course is 2 times 10 to the 30th kilograms. We have to convert that to grams for this particular problem. And of course, there's 1,000 grams in 1 kilogram. The kilograms cancel, and so that becomes 2 times 10 to the 30th times 10 to the third. So you just add the exponents, so it becomes 2 times 10 to the 33rd grams, and then you use that. In other words, whatever this answer is right here, that goes here into the volume, and then this, of course, is the mass, and that goes into the numerator, right? That's going to be our all right. So that's problem number 1. All right, here's number 2. So the escape velocity. They want to know the first part. This is actually part A. I should indicate that this one's part A. All right, so the general equation, of course, is the escape velocity equation. This is going to be the escape velocity from a white dwarf. So the first part is anyway. So we need, the mass of the white dwarf. They give us that's going to be the mass of the sun. They give us the size of the white dwarf, the radius of the white dwarf. The mass, of course, has to be in kilograms, and the radius has to be in meters. Remember, that's the way that works for the escape velocity equation. The escape velocity, of course, is always in meters per second. All right, so let's start out here. So they give us the radius of the white dwarf is 10,000 kilometers, or 1 times 10 to the fourth meters. So we have to convert that from meters to from kilometers to meters. So there's 10 to the third, or 1,000 kilometers. It's 1,000 meters in 1 kilometer. So the kilometers cancel. All right, so kilometers will cancel here in the denominator, and that will give us, it's just 1 times 10 to the fourth times 10 to the third, which is, you just add the exponents. 10 to the fourth times, times 10 to the third would be 10 to the seventh. All right. So then the escape velocity equation I have down here, written with the numbers in it, would be 2 times, times big G, which is always the same. It's a universal constant, the universal gravitational constant, 6.67 times 10 to the minus 11th. And remember, this is all under the square root, times the mass of the sun in kilograms, which of course is 2 times 10 to the 30th kilograms, and then divided by 1 times 10 to the 7th meters, right? That would be the size of the white dwarf. All right, we'll do part B in just a second. All right, so here's 2B. So they give us that the radius of the neutron star is only 10 kilometers. Of course, we need to change that to meters, just like we did for the white dwarf. So 10 kilometers times 10 to the third becomes 10 to the fourth. Another way to write 10 to the fourth is 1 times 10 to the fourth. And they give us that the mass of the neutron star is 2 times 10 to the 30th, the mass of the sun. So we're going to put that in here for the escape velocity equation. So it's going to be 2 times 10 to the 30th. And of course that's kilograms. Let me just indicate that here, kilograms. And then we divide by the radius, which we just figured out, which was right here. 1 times 10 to the fourth, right? So we're going to put that down here. 1 times 10 to the fourth, and of course that's meters. All right, I just have one quick note. The mass of the neutron star they give us is 2 times 10 to the 30th, but note, from the chapter, right, from chapter 15, and I discussed this, the mass of the neutron star has to be 1.4 times the mass of the sun, which of course it's not here. This is just an example. You would normally, if it's truly a neutron star, it would be at least 1.4 times the mass of the sun, and then the maximum it can be would be 3 times 10 to the 3 times 10 to the mass of the sun. All right, so that's just a little very interesting little part. All right, so we're going to do number 4 next. All right, so here's number 4. They ask us, how many neutrons are in a neutron star. So they give us the mass of the neutron star that's given to us in the problem, and they give us the mass of a single neutron. So really, we are going to use this equation. The mass of a neutron star is equal to n, which is n turns out to be the number of neutrons times the mass of one single neutron. So really the equation that you just manipulate this equation slightly, and so n, which is what you're solving for, is going to equal the mass of the neutron star, that's ns, mass of the neutron star divided by the mass of a single neutron. All right, so that'll give you the answer is just a pure number, because both of these are going to be in kilograms. The kilograms cancel, and that'll just give you a pure number of neutrons. Number of neutrons. All right, so that's how you do number 4. All right, so number 5, there's a couple of parts. One is that we want to find the side of a cube of neutrons if the cube was had as many neutrons as a neutron star. So you're given the volume of a single neutron. All right, so the volume of a single neutron turns out to be 1 times 10 to the minus 45th cubic meters. Okay, so that's important. That it's in cubic meters here. From this is supposed to say from problem 4, you discover that the number of neutrons in a neutron star is 2 times 10 to the 57th. Right, that's just a pure number. So that's just the number of neutrons in a neutron star. Remember, which is what you calculated from problem number 4. All right, so the way that you do this one is the volume of a cube is equal to this n, that comes from problem 4, times the volume of a single neutron, which is given to us in the problem, right? So this becomes, let me write this out real quick. This is going to be 2 times 10 to the, that's supposed to be times, geez, doesn't look very nice, times 10 to the 57th, and then times this volume of a single neutron, which is 1 times 10 to the minus 45th. And the thing that's important about that is that this is in cubic meters, right? Cubic meters. So that'll be the volume of a cube of, if the neutron star was shaped into a cube, which of course is impossible. They're just asking you this, this hypothetical problem. Anyhow, they want to really know what the side of one side of the cube is, and of course, for a cube, all 3 sides are the same distance, and so you just take whatever this number turns out to be, and you just take the cube root of that, right? And so you're going to put that the number right here, right, and take the cube root. All right, and then of course there's a part B. I'll do that in just a second. All right, so here's the second part of this problem number 5. So they give us that just recall that the radius of a neutron star is 10 kilometers, which is 10 times 10 to the third meters. So we need it to be in meters this time. So that's 1 times 10 to the fourth meters, and of course the diameter of they ask us what the diameter would be, is just 2 times the radius, the diameter of the neutron star. So that would be 2 times 1 times 10 to the fourth, or another way of saying that would be 2 times 10 to the fourth, or 20,000 meters. All right, and that being said, they want us to know, how many more times closer are the neutrons packed into the neutron star than they are in the cube. All right, so what we'd have to do is figure out what the volume of the neutron star is in cubic meters this time. All right, so if this is the radius, 1 times 10 to the fourth cubic meters, you cube that and multiply by 4 pi over 3, and you get this, about 4.19 times 10 to the 12th cubic meters. You use that and then divide by the volume in the cube that you discovered in part, the first part of problem 5, and so they come out to be pretty close. Of course, the volume of the cube is smaller, and you're going to get some number. It's a very low number, a little greater than 1, less than 3. So that'll give you the number of times closer the neutrons are packed into the neutron star than they would be in this theoretical cube. All right, so all right, the next one is number 7, a Schwarzschild radius. So let's start that. All right, so the Schwarzschild radius is actually one of the simplest of all the equations. So R, which is going to, the answer will be in meters, is equal to 2g times m divided by c squared. Now g and c are of course constants, and so the only variable here is the mass. So they give us the, what would the size of the sun be if it were turned into a black hole? Now remember, this can never happen with the sun, because it's not, after it dies, it's not going to turn into 3 times the mass of the sun. But this is a theoretical type problem. So 2 times big G times the mass of the sun divided by the speed of light squared. All right, so you'll get a number. It's a little less than 3,000. The answer, just to give you a little more of a hint, meters. All right, so it's a pretty simple problem. All right, let me do. Oh, you know what? I'm going to have to do number 9.